All right, once again, we are talking about internet addresses today. So, like we discussed last class, the core functionality of the internet, what it's really designed for, is sending information. So, from one computer, we want to send a smiley face to another computer, from one node on this tree to another node. So we follow a path, and we can actually send some information. And we discussed the mechanics of this, how it works, last class. Now, this class, we're going to talk about how those two computers are actually able to locate each other through this huge tangle of networks that is the internet. So every single device that is connected to the internet needs to have a unique address that is going to refer to only that device, so that anytime another device is looking to find it, they're able to connect to each other. And this is very similar to how we have a mailing address. Everyone has a unique address, or at least their home has a unique address where they can receive the mail from the mailman, so that they can have the postage delivered to them. So, as an example of a mailing address, let's look at Valley's address. We can see all these different elements. We have 100 Skyway Drive, San Jose, California, 95111, USA. So there are increasing levels of specificity within this address. The least specific thing is the country. So first thing, that's the broadest thing within this address, is which country are we in? So we are in the USA. The next level of specificity is the state within that country. We're in California. So we're narrowing down our possible areas. Next, we're in San Jose, which is this area in California. As we get even narrower, we're in the zip code 95111, which I would look, if you look on Google Maps, you can see what the borders of this zip code are. So this address is within this small area of San Jose. As we zoom in even further, we can find Skyway Drive. Zoom in, this is all of Skyway Drive that is within this, within that zip code. Skyway Drive does extend further beyond Monterey Road, but after Monterey, we are no longer in that zip code. And then this number is the most specific thing. That is a specific location on Skyway Drive where we are going to locate Valley Christian Schools. This is, I think, where the stadium is. That is our school's proper address. So you can see within a mailing address, we get increasingly specific till we have an exact location where we can deliver things. And the same is very similar on the internet, because every single device on the internet needs to have a unique internet address, so that every device can be uniquely identified and messages can be sent to or from that device. So anytime we send information using the internet, we have both a to and a from address. Just like when we are addressing a letter that we want to send, we need to send to whoever we want to send it to. And we also need to mark who it's from, so that the Postal Service can return it if they're not able to deliver it properly. Now, internet addresses are going to follow a standard agreed upon format called the Internet Protocol, which is often shortened to IP. And this protocol is going to define the layout of internet addresses, which are most commonly referred to as IP addresses. You've probably heard that term before. So let's look at this IP address. We have the IP address 93.184.216.34. So let's look at what each of those numbers represents. The first thing to note is, like a mailing address, we can go number by number, section by section, and we're going to hone in on a specific device with increasing specificity. So within our 4 numbers, that first number is going to represent which network we're connected to. That second one is going to be which sub-network. Third number is the sub-network. And our final number is which device on that sub-network we are looking at. So if we look at this tree again, the internet is a bit more complex than just this tree, but serves as a good example. So let's say this branch is the 93 section of the tree. Within that section, we can find the 184 section, and then hone in on the 216 section. And finally, this is device number 34 within that section of that section of that section of the internet. So we're honing in more and more specifically on that individual device. All right, does that all make sense so far? Cool, all right. So one great thing about the IP address system is that it's super scalable. It's very easy to add more networks and devices because each one just is going to get a new number from the list of possible numbers. Just like any numeric value, we're able to translate an IP address into binary. Each digit, or each number within an IP address can be represented by 8 bits. So the largest number for any of these is going to be 255. So yeah, like I said, we are going to represent each bit or each section with 8 bits. So our smallest possible IP address is 0000. Our biggest one is 255, 255, 255, 255. There we go. Now, if we get rid of the period and spaces here, we're left with a 32-bit binary number representing that IP address. And when we have a 32-bit number, that means we have a maximum of 2 to the 32nd total different unique IP addresses, which is over 4 billion. Now, if you remember back to last class and when we discussed how many different users there are on the internet right now, you might see a problem arising. So this 32-bit version of IP addresses is known as IPv4. That is the name of this standard. And it's been around since the 80s, back when the internet was first getting created. Now, back then, they did not know how popular the internet was going to become. They didn't realize it was going to be such an enormous worldwide hit. So as the internet grew and grew, it ended up being way more popular than expected. They thought 2 to the 32nd unique addresses, that's going to be plenty. There's no way 4 billion devices are ever going to be connected to the internet. Unfortunately, they were wrong. So because of this, a new protocol is being put in place to accommodate for this lack of unique numbers, unique addresses. We need more. Well, so the new standard being put in place is called IPv6, and it is currently being swapped in for IPv4. We're transitioning still. In this IPv6 protocol, every single device is going to have an address that consists of 8 4-digit numbers in hexadecimal. For example, this long sequence of numbers and letters. Now, this is obviously a little bit more difficult to say than an IPv4 address because it's significantly longer, but it also can have a lot more information. So who remembers how many bits we can use to represent each hexadecimal digit? And if you're holding up a hand, I can't see you because I'm recording and I don't want faces in the recording. So put it in chat. How many bits can we use to represent one hexadecimal digit?
4?
The answer is 4, correct. So if we do some multiplication, we have 8 clusters of numbers, we have 4 digits per cluster, and we have 4 bits per digit, which is, when we multiply that all through, that gives us 128 total bits. So when we put 2 to the power of 128, we get this number, which is absolutely massive. If you count it out, 100, 1,000, million, billion, trillion, quadrillion, etc., we get to 340 undecillion. That's 11 illion, I guess, is the number here, which is absolutely enormous. So the reason we have gone to this number is to try and future-proof our internet system, so that no matter how many people, no matter how many devices get added to the internet, we will still have enough unique addresses for every single one. Now, IPv6 is going to use that same hierarchical structure where it gets increasingly specific as we move onward. As IPv4, it just has more possible combinations because we have so many more digits and so many more bits. If you're curious as to why we jumped from IPv4 to IPv6 and just kind of skipped IPv5, the answer is because but when a different protocol was being developed, IPv5, it was under development, but it also had the same exact number of bits as IPv4. So it didn't really solve the problem that was being surfaced by IPv4 in not having enough addresses. So since the name IPv5 was already taken, moved to IPv6, which has this updated number of addresses. So that's why we're on 6 instead of 5. Now, the question is, who decides these things? Who is in charge of making these protocols? And the answer is there's a group of people who are known as the Internet Engineering Task Force, or IETF. And they are responsible for making these kinds of decisions. So the IETF is an open community of engineers, designers, vendors, and researchers who are concerned with the evolution and continued smooth functioning of the internet. Actually, they're all volunteers. This is a volunteer organization who are in charge of figuring out how the internet is meant to work. And it's open to apply for anyone. Anyone is welcome to try and become part of this IETF organization, which is pretty cool. All right. Does that all make sense? Internet addressing, how we can find unique devices on the internet? Any questions? Cool. All right.